Okay, students, in few question papers as well as in few textbooks, we have numericals as well on the defects of eye, that is myopia and hypermetropia, where some simple problems they have asked. Okay, so earlier we have discussed the formula. Okay, that is to find the focal length of the new convex lens in hypermetropia, and what is the focal length of the concave lens that was used in myopia, right? In myopia, f is supposed to be f is equal to minus x. Okay, that is minus x is the distance between the eye lens and the far point. Whereas in order to find out the focal length of hypermetropic eye, what was the formula? F is equal to x dash into d by x dash minus d. Okay, what do you mean by x dash? X dash was the distance between the eye lens and the near point, right? That is x dash of the defected eye. Okay, x dash is for the defected eye. Then small d means least distance of distinct vision. Okay, so x dash into d divided by x dash minus d gives the focal length of the hypermetropic eye. Always remember, for the myopic eye, focal length will always be negative. Why? Because f is equal to minus x. Whereas for hypermetropic eye, the focal length will always, means the corrected focal length will always be positive. The correction will all come, that is the focal length for the corrected hypermetropic eye will always come positive. Whereas for the corrected focal length for myopia or myopic eye comes negative. Okay, these things you have to remember. Now here we have first problem, you can see the near point of a hypermetropic eye. Now they have mentioned what type of problem it is, hypermetropic eye. Okay, that's why near point they have told. The near point of a hypermetropic eye is at 75 centimeter, which means you know, right? From the eye, what is the power of the lens required to enable him to read clearly a book held at 25 centimeter from the eye? 25 centimeter means that standard value, you know that is supposed to be the near point of a normal eye. Means the near point of a normal eye means least distance of distinct vision that is given. So you have a person with the myopic eye. Okay, now his near point n dash. Okay, the defected eye. So he is having the defected eye, and that near point is supposed to be 75 centimeter. Now he wants to read clearly a book which is held at 25 centimeter. Now this should be at 25 centimeter. Means this is supposed to be D, and this distance between the defected eye of a hypermetropic person or a person with a hypermetropia and this distance where he is not able to see the objects. Okay, that is, he is getting the blurred image. That is at 75 centimeter, which means this is supposed to be x dash and this is supposed to be the d. Okay, small d, and this is x dash. Now you got the description of the problem. Now you can write the given data, that is whatever it is given, then you can use the formula of the focal length. Okay, now what is the power of the lens required to enable him? You have to find out the power of the lens. In order to find the power of the lens, first you should get the focal length, right? Then you can take the reciprocal and find the power of the lens required to enable him to read clearly a book held at 25 centimeter from the eye. Okay, now what you have to do, write the given data, that is x dash is equal to 75 centimeter, then d is given, that is 25 centimeter. Now we have to find out what? First you have to find out focal length, then you have to find out power. Now for the focal length you have f is equal to, what is the formula? X dash into d divided by x dash minus d for hypermetropia, right? That is corrected focal length. F dash is equal to, what is x dash? 75 into 25 divided by 75 minus 25, or f is equal to 75 into 25 divided by, what you will get? 50, right? 1s are 2s are 4, 5s are 6, 7s are 8, 9s are 10, 11s are 12, 13s are 14, 15s are 16, 17s are 18, 19s are 20, 21s are 22, 23s are 24, 25s are 26, 27s are 28, 29s are 30, 31s are 32, 33s are 34, 35s are 36, 37s are 38, 39s are 40, 41s are 42, 43s are 44, 45s are 46, 47s are 48, 49s are 50. Right? 1s are 2s are Then what you will get? 2 1s are, 2 3s are, 2 7s are, then 2 5s are. Focal length is equal to 37. It is always positive, remember, 37.5 centimeter. Now you will have the doubt. Why we should not take negative signs here? Because we are taking the measurement from the defected lens. Remember, we have all in the formula, while beginning with the formula, that is 1 by f is equal to 1 by v minus 1 by u, there only we have substituted minus x dash and minus d. Then we got this formula x dash into dy x dash minus d. So in the problem, if they give the values of x dash and d, don't take negative sign, because already we have taken the negative sign and come up with the resultant formula. Okay, so take the numbers as it is. So we will get the focal length to be a positive value. When the focal length is said to be a positive value, means it clearly says that the person is having hypermetropic eye, and for the correction we have used convex lens. Okay, now we have to find out what? We have to find out the power of the lens. Therefore, power of the lens P is equal to what? We have to use this in centimeter. It is given, it is 100 by f. So P is equal to 100 divided by 37.5. So what you can write this as? P is equal to 100 divided by 375 by 10, or when it goes up, P is equal to 1000. Okay, because 100 when it goes to 10 goes to numerator means 1000 it will get, you will get 375, or P is equal to what you will get? 0.375. Okay, P is equal to 0.375. Okay. Sorry, you will get the value of P is equal to, when you simplify this, you will get equal to 2.66. Okay, you will get 2.66. Now this power is measured in diopter. So what you will get the value of power? 2.66. That is positive. Why we have got positive means focal length we have got positive. That's why you will get the power in, the power value is positive. 2.66 diopter is the answer. Thank you. Okay, moving to the second problem, you can see here. A person cannot see the objects distinctly when placed at a distance less than 100 centimeter. What is the power of the spectacles that he should use to see clearly the objects placed at 25 centimeter? So when you see the problem as well as when you read the problem, the statement of the problem, you will come to know that the person is having hypermetropia. Right? It's not myopia, it is hypermetropia. Why? Because you can see here, the person at exactly 75 centimeters, okay, he cannot see the object distinctly when placed at a distance less than 100 centimeter. Now see here, it's not 75. Now see here, 100. Now let us set the hypermetropia means near point. That near point, let us set it as 100 centimeter. Now, he is not able to see the objects at the near point as well as less than the near point of the defected eye. Near point doesn't mean for the normal eye. Near point for the defected eye, that is n dash. Okay, now it is n dash here. Okay, now here the eye lens is there. Okay, in front of it you will get corrected eye lens, that is convex lens. Now here n dash we have set it is for 100 centimeter. Now this fellow is having hypermetropia. He cannot see the objects which is less than this 100 centimeter. Okay, so that problem is having. Now what is the power of the spectacles? Okay, if you want to use the spectacles, what power it should be? That he should use to see clearly the objects placed at 25 centimeter. Why? Because 25 centimeter is the least distance of distinct vision that we can have. Okay, so at exactly 25 centimeter at here, so this is n dash and this will be n of the normal eye. Okay, that is n means here it is 25 centimeter, means this value is d. So in order to read normally, the person should be in least distance of distinct vision. So what power of the spectacles he has to use? Means suppose if at all we are placing a convex lens. Okay, what is that power of the convex lens, that particular convex lens used in the spectacles? Okay, to use clearly, to see the objects clearly at 25 centimeter. So obviously this 25 centimeter is small d, that is least distance of distinct vision of a normal eye. Now this is defected eye, that is 100 centimeter. Now this will become what? X dash. Now we have x dash and d, then you can find out the value of focal length of the corrected convex lens and also the power of the convex lens. So for which you have to use the formula, right? Therefore, what is given? We have x dash is equal to 100 centimeter. Then we have d is equal to 25 centimeter. Find the focal length. So focal length, that is corrected focal length, which is equal to x dash into d divided by x dash minus d. What is x dash? 100 into 25 divided by 100 minus 25, or f is equal to 100 into 25 divided by, what is 100 minus 25? You will get 75, right? 25 ones are, then 3s are. Then what you will get? F is equal to 3 ones are, 3 3s are, then again 3 3s are, 0.3. You will get recurring decimal. So focal length f is equal to, what you will get? Plus 33.3 centimeter. Now this is the focal length that you have got. Now you have to find out the power of this particular lens, that is convex lens, corrected convex lens. So f is equal to, P is equal to 100 by f. Okay, now P is equal to, what you will get? 100 divided by f is 33.3 centimeter, or I can, if I want to remove this decimal point, what I should do? 100 divided by 333 by 10, because after decimal point one place, this goes to numerator. P is equal to 100 into 10 means 1000 divided by 333. Now if you simplify it, you will get the value equal to, P is equal to 3 diopter. Okay, P is equal to 3 diopter, approximately equal to 3 diopter, because 333 into 3, if you do 3 3s are 9, 3 3s are 9, 3 999, because here you have 1000, right? So you will get 2 point something, 2.99 something, exactly you will get it as, we can approximate that equal to 3 diopter. So that person should use the spectacles made out of the convex lens with the corrective focal length of plus 33.3 and the power of the lens equal to 3 diopters. Okay. Now the third problem, though the problem seems to be looking very big, but the answers are very easy. Just read the description of the problem. Now this was in CBSE, one of the sample papers. Okay, a student suffering from myopia. They have only mentioned that the student is having myopia. Okay, the student suffering from myopia is not able to see distinctly the objects placed beyond 5 meter. Okay, so beyond 5 meter means far point is 5 meter here. So beyond that he is not able to see the objects. List the possible reasons due to which this defect of vision, these defects of vision may have arisen with the help of ray diagrams. So means you have to draw those 3 ray diagrams of myopia. 3 ray diagrams is there. Okay, normal eye, myopic eye, and correction for the myopia. So all these ray diagrams you have to draw. Okay. Now, what is the 2 possible reasons for which the person or the student is not able to see the objects placed beyond 5 meter? Okay, means the reasons for the myopia. One is what? Increase in the curvature of the eye. What? Increase in the curvature, okay, of the retina. So that length of the full retina or the increase in the curvature of the eyeball. So that is one. One more thing is decrease in the focal length. Okay, increase in the length of the curvature, increase in the length of the curvature and decrease in the focal length. So these two are the possible reasons for the person who is having the myopic eye. Okay. Now, why the student is unable to see distinctly the object beyond 5 meters from his eyes? So I have told the reasons. Why? Because of the increase in the length of the curvature and decrease in the focal length. Now, the type of corrective lens used to restore proper vision and how this defect is corrected by the use of this lens. In the ray diagrams itself, you will come to know that the type of corrective lens used is what? That is second one. The type of corrective lens used is what? Which lens? Concave lens is the corrective lens that it has to be used. Okay. Now, if in this case, now what happens and how this defect, in the second case only you can see, and how this defect is corrected by the use of this lens. Now what happens before use of this lens in myopic eye? What happens? The blurred image is formed in front of the retina, not on the retina. So what happens if you use the corrective convex lens of suitable power? So the image is exactly formed on the retina. Okay, so that is the how to correct this defect. Suppose if you use the concave lens of suitable power, this defect is corrected when the blurred image or when the image is exactly on the retina. Okay. Now third one, if in this case the numerical value of the focal length of the corrective lens is 5 meter, means numerical value of the focal length is given, that is 5 meter. Okay. Now find the power of the lens as per the new Cartesian sign convention. So here what you will get? Here the focal length is given 5 meters. Okay. Now just recall the focal length of the corrective lens in myopic or in myopia. Always the focal length will come negative, right? So you have to take this 5 meter as negative, minus 5, because f is equal to minus x, right? So that x value is 5 meter, so f is equal to minus 5 meter. Therefore you have to find out what? Power. So therefore power is equal to, since it is in meters, let it be in meter only. Don't go for p is equal to 100 by f, don't use that, you will use only 1 by f. So what you will get? P is equal to 1 by f, the 1 divided by minus 5, or p is equal to minus 1 by 5, or p is equal to what you will get? Minus 0.2 diopter. Okay, minus 0.2 diopter is the power of the corrective lens, that is concave lens. What power he should means? That student should wear the spectacles. Okay, the student should wear the spectacles made out of the corrective lens, that is concave lens, having the power minus 0.2 diopter. So the problem seems to be more because of seeing the wordings of the problems, but the answers are supposed to be very easy and precise. Okay. Now moving to the fourth problem. Nooper needs a lens of power minus 4.5 diopter for correction of her vision. Okay, it is minus 4.5 diopter for correction of her vision. First case, what kind of defect in vision is she suffering from? Means what defect she is having. Now it clearly indicates that since power is negative, she is suffering from myopia. Yes, therefore she has a myopia or myopic eye. Okay. Now B. What is the focal length and nature of the corrective lens? Okay. Nature of the corrective lens only you know. For myopia, what lens is used? We use concave lens. Okay. Now, what is its focal length? We have to find out focal length. Therefore, we know that P is equal to P is equal to 100 by F. Okay. Or F is equal to 100 by P. What you will get? 100 divided by P is, now here P is how much? Minus 4.5 diopter. P is minus 4.5 diopter. So 100 by minus 4.5. 5. So what you can write, our P is equal to, or F is equal to, so I'll shift this minus sign to the numerator. So what you get, minus 100 by, this 4.5 can be written as 45 by 10. Bring this to numerator. F is equal to 100 into 10 is 1000 divided by 45. When you simplify, you will get the focal length, which is equal to minus 22.2 centimeter. Minus 22.2 centimeter. Now you got the focal length to be negative. Why? Because power is negative, corrective lens is concave lens. Now you have to find out. Now see, you can see, draw the ray diagrams. So you know how to draw the ray diagrams of the myopia. Okay, those 3 ray diagrams you have to draw. What are the causes for this defect? So what are the possible causes for the myopia? One is increase in the curvature of the retina or increase in the curvature of the eyeball. Okay, so that curvature increases, then decrease in the focal length. So increase in the length of the curvature of the eye or the retina and decrease in the focal length are the reasons or the causes for this defect. Okay. Now you can see the 5th problem. The myopic person can see the things. So what kind of person? The myopic person can see the things clearly only when they lie between 10 centimeter and 100 centimeter from the eye. Which lens will enable him to see the moon clearly? Now see here. Now you have a myopic person here. Okay. Now you have a myopic person. Now here it is 10 centimeter. Okay. Here it is 10 centimeter. Now here it is 100 centimeter. Now 10 centimeter and 100 centimeter. Now he can see the things clearly only when they lie between 10 and 100. Now see here, he can see the things only if the objects they lie between 10 and 100 centimeter. Which means this is supposed to be, now they have given like range. Okay, range of the vision they have mentioned in the problem. Now this is supposed to be the near point. Okay, and this is supposed to be the far point. Now this is supposed to be this is near point and this is far point. Okay, just assume. Okay, now here we have the range. Okay, and they have also given that the person is myopic. They have, in the problem mode, it is given that he is having myopic vision. So which is the corrective lens used? Concave lens. Simple. Which lens will enable him to see the moon clearly? Now moon is somewhere here, very very far. Okay. Now which lens will enable him to see the moon clearly? Okay. Now here it is moon. Now which lens will be is able to see the moon clearly? Now moon is still at a far distance. Okay. At a very far distance now. Okay. Beyond 100 centimeter. Now which lens he has to use in order to see the moon clearly? Now what happens? The far point is given. Okay. 100 centimeter. That you should consider. You have to just find the power of the lens here. Okay. Now since it is myopia, okay, since it is myopia, you have to find out what power of the lens. Now this is given, that is that f is nothing but what? Minus x as per the formula, focal length. Because it is myopia, it will come negative. That minus x is nothing but what? This 100. Okay, what you will get? Minus 100 centimeter is the f. Don't go for this near point. Concentrate only on far point now. Why? Because he has to see the moon. Moon means, again, moon is at a very too large distance, right? The distance between the person on the earth and the moon is very far. So when we speak of far distances means, always remember that he is a myopic person and the corrective lens that has to be used is concave lens. Okay. Now what is the corrective lens that has to be used is concave lens. Now just find the power for this. Okay. You have to find out the power. Now formula for power is P is equal to 100 by f, or P is equal to 100 divided by this f, that is 4 point, is given as minus 100. It gets simplified. P is equal to minus 1 diopter. So he has to use a concave lens with the power of minus 1 diopter. If we use that particular lens in the spectacles, he can clearly see the moon, which is at a very far distance from the observer. Okay. Moving to the sixth problem. A person can see objects lying between 25 centimeter and 10 meter from his eye. His vision can be corrected by using lens of power minus 0.1 diopter. Is this statement true or false? So it is like a true or false question. You cannot blindly say because the range is given and use of they have only given the power of the lens use minus 0.1 diopter. You cannot say blindly either true or false. You have to verify it. Okay. Now just observe the problem. There is a person. Okay. Now this person is capable of seeing the objects between 25 centimeter. Okay. The objects between 25 centimeter at this and 10 meter. Now assume that here it is 10 meter. Means within this range he is able to see the objects. Okay. Now his vision can be corrected by using the lens of the power minus 0.1 diopter. Whether this statement is true or false, we have to see here. Now they have given the power in negative. They have given the power in negative, that is minus 0.1 diopter. That itself is the clue that is given, like that person is suffering from which type of eye defect. Okay. Since the power is negative, that is minus 0.1 diopter, this person is having myopia, right? This person is having what? He is having myopia. Now, the range is again being given, right? Now, this is for a myopic person. What is the distance? Now, this is the far point and this is the near point. We don't want near point, we want only the far point, okay? We want only the far point. Now, he is having the myopia and we have got the far point. Now, whether we have to confirm whether that corrective lens, what is the corrective lens used for a myopic eye? It is concave lens. So, that power of that concave lens, whether it is minus 0.1 D or not, we have to verify. Now, we have got here, therefore, we have got this focal length f is equal to minus x, right? This is x now. From here to here it is x. Now that x is nothing but what? Here it is given minus 10 meters. So convert that to centimeter. You know that 1 meter is equal to 100 centimeter. Therefore, f is equal to minus x, which is equal to minus 10 into 100, that is minus 1000 centimeter. Now focal length is supposed to be minus 1000 centimeter. Now you know the formula between the relationship between power and the focal length. Therefore, P is equal to 100 by F. Therefore, P is equal to 100 divided by, what is F here? It is minus 1000, or I can write this minus sign to the numerator. So minus 100 divided by 1000, 2 zeros goes off, 2 zeros goes off. So what you will get? Minus 1 by 10. What? Minus 1 by 10 means what? You get minus 0.1 diopter. So what is the question? They have given the power, that is his vision can be corrected by using lens of minus 0.1 diopter. Now the tally, you just make, just see here, both are the same values. We have got the correct value. Therefore, this statement is true. Therefore, the statement is true. Statement is true. And if the power is coming negative, means what type of lens that he has used? For corrective lens, that is concave lens. Why? Because he is having myopia. Okay. To the seventh problem, you can see the distance of the distinct vision. Remember, students, don't confuse. Please read the sentence what they have given. the distance of the distinct vision. It is not least distance. It is not least. Least is not the word mentioned here. They have mentioned only the distance of distinct vision of a person is plus 50 centimeter or 50 centimeter. He wants to read a book placed at 25 centimeter. What should be the focal length of the spectacles? Which means you can see here the distance of the distinct vision of the person is 50 centimeter. Now here you have a person. Now he is having the distance of the distinct vision, means that far point. Okay. Sorry, not far point, that is n dash. N dash they have mentioned. Okay. Means here only you should get the idea that it is related to hypermetropia. Okay. Now that n dash is given, that is 50 centimeter. Okay. Now he wants to read a book placed at 25 centimeter. Now here it is 25 centimeter. So he wants to read the book which is placed at 25 centimeter. That 25 centimeter is nothing but what? N. For a normal eye, the least distance of distinct vision, that is D, is given 25 centimeter. This 50 centimeter is X dash. Okay, X dash, that is from the eye lens, from the defected eye lens till the N dash, means from where actually it is getting the view at N dash, the defected eye lens. So that's why it is N dash and it is 58 centimeter. It is more, X dash is always greater, right? Now that N value or the normal eye can have the least distance of distinct vision, they have mentioned, that is 25 centimeter. Now we have to find out what should be the focal length of the spectacles. Now here we should get into the groove of the problem, that is this person is having what? Hypermetropia. This person is having hypermetropia. Then you can have the data, that is X dash is given, which is equal to 50 centimeter. Then small d, which is given 25 centimeter. You have to find out what? The focal length. Now you have the focal length formula. F is equals to X dash into d by X dash minus t, or F is equal to 50 into 25 divided by 50 minus 25, which is equal to into 25 divided by, what is 50 minus 25? It is 25. Then focal length is equal to 50 centimeter. Now what is the focal length value? The focal length value what you got is 50 centimeter. What should be the focal length of the spectacles? The focal length of the spectacles should be 50 centimeters. Now let us move to the next concept, that is refraction of light through prism. Okay. Before going to the refraction of light through prism, so this concept can be compared to the refraction of light through a glass slab. That is two refraction what we have studied in a glass slab, where we studied the concept of lateral shift. There the light ray underwent two refractions within the glass slab, right? On the opposite faces of the glass slab, it underwent two refractions. That is, the ray of light first came from the rarer medium, entered into the denser medium, and again from the denser medium, it finally emerges out of the rarer medium. So this we saw in the two refractions in the rectangular glass slab. The same way here also, in place of rectangular glass slab, here we have a prism. Okay. Now, of course, the properties of prism is quite different, or it is entirely different from the normal, that is the properties of the rectangular glass slab. Okay. However, even this prism supports the refraction. Okay. Now, what is this prism? You can see here a prism or a triangular glass prism. What we have used is a triangular glass prism, which is made up of two triangular bases. Okay, two triangular bases. Okay, you can see here ABC is one triangle, DFE is one more triangle, opposite. Okay, they are opposite. So they act as a base. Okay, they are the basis of the prism, as well as it is also made up of three rectangular faces, and these three rectangular faces will support the refraction. Okay, now you can see which are those three rectangular faces in this figure. A, C, E, D. One rectangular face. It is like this. Next, A, B, F, D. It is towards like this. Okay, one more rectangular face. One more rectangular face is B, F, E, C. Is one more rectangular face. So three rectangular faces, or you can say it as three rectangular lateral surfaces. Three rectangular lateral surfaces and two triangular bases. So this comprises of that is triangular glass prism. Now here we can see here it is resting on one of the base. Okay, it is resting on one of the triangular base. I have named A, B, C. Okay. Now here you know that if this is the triangular base, sorry, if this is the triangular base, here you will find one rectangular lateral surface. To the right side, one more rectangular lateral surface. Now at the base, one more rectangular lateral surface. Now the two rectangular lateral surfaces which are present along the sides AB and AC supports refraction. So prism supports refraction. You can see here outside the prism is a rarer medium, that is air. The prism itself is made up of a glass, that's why it's also called as glass prism. It is denser medium, and again to the right side again you have the air, which is rarer medium. Now see here, now this ray of light is incident at some point on the side AB, okay, of the prism, on the edge of the lateral surface, that is AB of the prism, at this point where I have drawn a normal N dash. N dash is a normal drawn to the edge AB. Okay, now that's why it is 90 degree. Normal is always drawn perpendicular. To this normal, at this point, the incident ray is coming from the rarer medium, that is air. It is incident at this point. Naturally, the refracted ray within the prism should be deviate the path, right? The refraction should happen, means the ray should bend its path. It should deviate the path, right? See here, it is coming in this direction within the prism. You can see the refracted ray which is bent, and it is bent towards the normal. It is bent towards the normal. Why? Because the incident light is coming from rarer to denser medium. So when it comes from rarer to denser medium, the refracted ray bends towards the normal N dash. Now again this refracted ray within the prism ABC is moving and striking on the opposite edge, that is AC, of the other lateral surface, or opposite lateral surface, rectangular lateral surface that having edge, that is AC, it is striking, which means now that refracted ray itself is acting as an incident ray along the edge AC. Again you have to draw one more normal N dash for the edge AC, which should be perpendicular. N dash should be drawn normal perpendicular to this edge, just like here. Okay. Now you can see here this refracted ray is moving here and it is striking this AC at some point. Okay. Again, you know, now this refracted ray is acting like an incident ray, right, for the side or for the edge AC, which means that ray is within the glass. Glass is what? Denser medium. Next medium outside of the glass is rarer medium. So when a ray of light travels from denser medium to rarer medium, it emerges out, right? Finally it should emerge. That ray is called as what? Emergent ray. You can see here, this is the emergent ray. Okay. Now that emergent ray is making an angle E with the normal N dash. See the angle of emergence. Angle of emergence you can see. Angle of refraction also you can see. Okay. So this is the angle of emergence. This is the angle of refraction. Sorry. This is the angle of emergence. This is the angle of incidence. I is the angle of incidence. R is the angle of refraction. And E is the angle of emergence. Now see here. And this angle, this emergent ray is moving away from the normal. Okay, it is moving away from the normal, whereas the refracted ray within the prism is towards the normal. Okay, this is away from the normal, it is towards the normal. Now what you have to do? Suppose, see the incident ray I. Okay, sorry, the angle of incidence. Now this is incident ray. This incident ray, if there was no prism, assume, okay, there was no prism, air was the only medium, right? Then you would have had only the air being only the single medium. In that medium, the light, the incident ray would have traveled straight. You can see here, undeviated incident ray. In the absence of the prism, the incident light in the single medium, that is air, it would have traveled straight. That's why it is called as undeviated ray. Now what you have to do, you just produce back this emergent ray, okay, backwards, so that it will intersect at some point on the undeviated ray. Okay, produce this emergent ray backwards so that it will meet or intersect at some point on this undeviated ray. So these two rays, that is the emergent ray produced backwards, when it meets a point on the undeviated ray, will make an angle, what we call it as angle D. That angle D is called as angle of deviation. So, which are the angles now which we have seen in this glass prism or the refraction through the glass prism? First one is angle A. You can see here this angle A. This angle A is also called as angle of the prism. Angle A is called angle of the prism, or it is also called as principal angle of the prism. So very important. This A is called angle of the prism or principal angle of the prism. Then I is called as angle of incidence. R is called as angle of refraction. E is called as angle of emergence. Now what is the relationship that binds the angle of prism, angle of refraction, incident angle, then angle of emergence and angle of deviation? D is angle of deviation. All these four angles are bounded by a relation. You can see here, angle A plus angle D is equal to angle I plus angle E, which means sum of principal angle and the angle of deviation is equal to the sum of angle of incidence and the angle of emergence. We can even do a small experiment with the prism and we can verify that these two angles, when you add it, it is equal to these two angles. So I repeat, the sum of angle of the prism and the angle of the deviation is equal to the sum of angle of incidence and angle of emergence. So these are the various things that we observe when the light undergoes refraction within the prism. Okay. Moving to the next concept, that is dispersion of white light by a glass prism. Now we have understood how refraction takes place in a prism using only single wavelength or single color or monochromatic light we have used there. Only single ray of light we have used, and we showed the normal refraction that takes place on both on the opposite lateral surfaces, that is rectangular lateral surfaces. Now we will do a small experiment here. What we will do, we will now incident a white light. You know, the white light, even though it looks white, within it is having certain colors of different wavelength, right, which is hidden in that white light. Now that comes out, okay, as separate colors in this dispersion. So what do you mean by dispersion? Dispersion is a phenomenon in which whenever a white light is passed through a prism, it splits up into the 7 colors. It splits up into its constituent 7 colors of different wavelength. I repeat, dispersion is a process in which a white light, upon passing through the prism, will split up into its constituent 7 colors, okay, which are having different wavelengths, okay, and this 7 colors are called as spectrum. These 7 colors are called as spectrum, and since this spectrum is visible by a human eye, you can see it, it is also called as visible spectrum, okay. This spectrum of 7 colors you can see here, okay, Vibgaya, that is violet, indigo, blue, green, yellow, orange, red, of different wavelengths is visible by a human eye, so that's why it's called as visible spectrum, okay. Now how exactly it happens we can see here. Now you take a sheet of paper and mark a small hole in it, okay, at the center of this paper, which is also called as pinhole. Make a small hole at the center of the paper or the sheet. Now make a white light to pass through that pinhole so that you will get a narrow beam. Okay, you will get a narrow incident beam on the edge AB of the prism. Okay, now you can see here this white light is the incident light which is passing through the pinhole of the sheet, and it is incident on one of the faces, that is one of the refracting surfaces of the prism, that is AB. Now what happens at this point only the refraction should take place, right? Now at the first stage itself, at the first lateral surface itself, this white lights will split up into the 7 different colors of different wavelength, okay, within the prism. Now you can see here, okay, now this first ray it is undeviated ray. Undeviated ray means in the absence of the prism, the white light would have traveled straight, okay, without any deviation, without any refraction. So in the presence of the prism, what happens at the interface? It is getting split up into 7 colors. Okay. Now again these 7 colors of different wavelength will hit the surface, that is lateral surface AC, refracting surface AC, one more opposite refracting surface AC of the prism. Now the outgoing rays which are called as emergent rays, and these emergent rays will result in the form of a spectrum. On the screen you can see you are able to get the spectrum of 7 colors of different wavelength. Okay. Now you can see here violet at the bottom, indigo, blue, green, yellow, orange, red at the top. Now you can see here this is undeviated ray, right? See, just we will make a comparison taking 2 wavelengths. Okay, which are the 2 wavelengths? One is I will take violet and the last one is red. First one is violet, last one is red. Now see here, this violet is this ray, last ray coming here. See the deviation, angle of deviation from the undeviated ray, from here to here, see. So the angle is very large, right? It means deviation is large, deviation is greater. Compared to what? Compared to this first color, that is red. Okay, you can see at the top color, this is bottom, this is topmost, that is red. See the deviation. The deviation is less, right? So deviation of the violet color is greater than the deviation of the red color. Okay, this is the observation that we are making here. Now you can see here, when the spectrum is formed consisting of 7 colors of different wavelength and different frequency also, violet, indigo, blue, green, yellow, orange, red, you can see here the violet is having the wavelength, lambda is called wavelength. Okay, now that wavelength is expressed in terms of angstrom. Okay, A upon it, if you write a small 0 means it is angstrom. So here it is, while for violet you have the wavelength 4000 angstrom. Now what is the relationship between angstrom and meter? You can see here 1 angstrom is equal to 10 to the power of minus 10 meter, means very less value. The value of angstrom in meter is very less. Okay, now 1 angstrom is equal to 10 power minus 10 meter, remember that. Now see here, for violet you have wavelength 4000 angstrom. See the frequency, these are the standard values. Okay, frequency is 7.5 into 10 power 14 hertz. Now see the top, the topmost color is what? Which is having less deviation, red color. See the wavelength, 7900 angstrom is the wavelength. See the frequency, 3.8 into 10 to the power of 14 hertz. So what conclusion or what observation that you are making here? You can see here, wavelength is lesser means frequency is more. Lesser the wavelength, greater the frequency. Now see here, lesser the wavelength, greater the frequency for violet. See for red color, see these 2 numbers, greater the wavelength is greater, okay, frequency is lesser, which means the wavelength and frequency are inversely proportional. Okay, so I repeat, lesser the wavelength, greater the frequency, greater the wavelength, lesser will be the frequency. Okay, also as I was explaining this spectrum, okay, means whenever the light is passing through the prism, it results in the spectrum of 7 colors of different wavelength frequencies, right? Now this spectrum consists of, it is of 2 types. One is pure spectrum and impure spectrum. Now what do you mean by pure spectrum? Pure spectrum is a spectrum in which all these 7 colors are distinct. Okay, they are not what? They are not mixed, okay? They are separate colors. Means you can easily differentiate between violet to indigo and between indigo and blue, between blue and green, between green and yellow, between yellow and orange, and between orange and red, okay? Means there is a distinction that you can make about all these 7 colors. So that is known as pure spectrum. Whatever the spectrum that we are seeing in the prism, okay, it is impure spectrum, where we can see overlapping of one wavelength on another wavelength, or overlapping of one color on another color, okay, which means the violet is getting mixed with or getting overlapped on indigo, the indigo which is overlapped on blue, the blue is overlapped on green, the green is overlapped on yellow, yellow being overlapped on orange, and orange being overlapped on red. So this results in impure spectrum. So usually we get the impure spectrum, okay. Now we know this relationship between refractive index, speed of light, and speed of light in any medium that we have learned in refraction, right? N is equal to C by V. Now what this indicates means, lesser the refractive index, compare only refractive index on speed of light in any other medium. Why? Because speed of light in air is standard value, air, vacuum or free space, 3 to 10 power 8 meter per second. Now just compare this N with the denominator, okay, here. Now more the refractive index, lesser will be the speed of light in that medium, or lesser the refractive index, more will be the speed of light in that medium. So with this relationship we can have some conclusions here. You can see here, which you can see the spectrum of 7 colors, violet, indigo, blue, green, yellow, orange, red. Just make a comparison for only 2 colors, taking 2 colors into that is for comparison. Consider only the first color violet and the last, that is on the top, that is red. Now among these 2 colors of wavelength, which color is having maximum deviation? You can see here, violet is having maximum deviation. Which is having least deviation? Red is having least deviation, means lesser angle. This is greater angle, that is violet is having greater angle from undeviated ray. So deviation of violet, this violet color, deviation of violet is greater than deviation of red, okay. So therefore, hence refractive index of violet is greater than refractive index of red. So angle of deviation is directly proportional to the refractive index. Angle of deviation is directly proportional to the refractive index. You can see here, more the deviation, more will be the refractive index. That's why refractive index of violet is greater than refractive index of red. Why? Deviation of violet is greater than deviation of red. But you know that this refractive index is inversely proportional to speed, right? Therefore, speed in the violet is less than speed in the red color, or speed of violet color is less than speed of the red color. So these are the important conclusions or the observations that we can make out in the dispersion of white light. Now what is the cause for the dispersion of wavelength? The cause for the dispersion of wavelength mainly because of the wavelength of the light, or the different wavelength present in the white light. So dispersion happens only because the white light constitutes the color, or by the white light has different wavelengths. So that is the reason for the dispersion. And dispersion is also dependent on various factors. That is, it depends on the refractive index of the medium. It is also depend on speed of light. Okay, sorry. It also depend on the speed of different colors of light. Okay. It is also dependent on the angle of deviation also. It is also dependent on angle of deviation. But the primary cause for the dispersion is the wavelengths. Okay.